Good morning, dear students. Welcome to this session on moment distribution method. So, last session we have derived the expression for carryover factor. Okay, what is the value of carryover factor and what is the value of carryover moment also. Okay, so carryover moment m dash we got it as applied moment divided by 2, half of the value of applied moment, and carryover factor is equal to 1 by 2. Okay, right. In this session we will see what is the expression for stiffness. Okay, so stiffness is already defined in the earlier sessions, like k is equal to m by theta. M is applied at a, hence theta is also theta a. So if you know this value, we can get stiffness formula, right? Theta AB, if you are able to evaluate, we will be able to find out stiffness value. So let us see how you get theta value from these expressions. So if you want theta A is now divided into two values, right? This is actually theta A from both m and m dash, theta A. But you have separated m and m dash. So hence you have to calculate theta A as the summation of theta A1 and theta A2 values along with their sign anyhow. So if they are of same direction, we will add. If they are of different direction, we will subtract, right? So theta A, if you want, you need to know what is theta A1, what is theta A2. So theta A1 is clockwise, positive. Theta A2 is anti-clockwise, negative. What is theta A1? ml by 3ei. Okay, got it. So theta A1 uh, value ml by 3ei, theta A1. Okay, so what is theta A2? M dash L by 6ei. So we want these two values. So theta A means theta A1 plus theta A2, whereas theta A1 is positive, whereas theta A2 negative. Reason, theta A1 is clockwise, theta A2 anti-clockwise. Theta A2 is anti-clockwise. That's why we use minus sign. So ml by 3ei, theta A1, m dash L by 6ei, which is theta A2. So theta A1, theta A2. Okay, so this is clockwise positive, whereas this is anti-clockwise minus. So we used minus sign. So what is m dash? Substitute m dash as m by 2. Okay, so ml by 3 ei minus ml by 12 ei. So 1 by 3 minus 1 by 12. Okay, so ml by ei common. So if you just see that 12 threes 36, let us say. So 3 12s 36 minus 12 threes. So what happens? 12 minus 3. Okay, so 9 by 36. Okay, so what happens is 12 minus 3 by 36. Okay, so 9 by 36 becomes 1 by 4. So ml by 4 ei is theta ea value. Okay, so individually they are ml by 3 ei and m dash l by 6 ei. But theta a means it is both from m and m dash. So that's why we get theta a as ml by 4 ei. So, okay, so what it is? Theta a means what? When you take a member, one end hinge, other end fix. If you apply moment m at the hinge end, the rotation of that end is equal to ml by 4 ei. So what is k? M by theta. So m divided by, substitute for theta. What is theta? M L by 4 E I. Okay. So M and M gets cancelled. So this will be reversed. 4 E I by L is equal to stiffness of the member. K is 4 EI by L. When it is, what are the conditions involved in this one? One end of the member should be hinged, near end hinge, far end fixed. Then only this value will be 4 ei by L. Okay, correct? So stiffness of a member when far end is fixed is equal to 4 ei by L. Okay, so we have solved the expression for stiffness from the very same diagrams that are being derived. Okay, for which is taken for the definitions, a member AB hinged at A, fixed at B, and applied by capital M moment at A is taken, and then that is being drawn with the partial free body diagram. And then the two moments are taken, one moment at successively we have taken M and M dash. Then we wrote moments and slope values. Then from slope values, so theta a, if you are able to calculate from slope values of applied by m and m dash, we will be getting theta a value, that is nothing but ml by 4 ei. So stiffness of the member when you apply moment, which is equal to 4 ei by L, and this value is for a case of member when far end is fixed. Okay, right. We'll come back to the remaining expression in the next session. Thank you.